Every year, typhoons dump staggering amounts of water on Tokyo in just a matter of hours. We're talking about hundreds of millions of liters falling on one of the largest metropolitan areas on Earth. So much water it could fill thousands of Olympic-sized swimming pools before you even finish this video. And yet, the city doesn't sink. How does a metropolitan region with more than 37 million people survive rainfall that would turn almost any other city into a flooded disaster zone? The answer is hidden where almost no one ever looks. Beneath soccer fields, under parking lots, below entire neighborhoods in Saitama, on the outskirts of Tokyo, there is a vast artificial river underground, a colossal structure that looks more like a secret temple carved out of concrete. A system so massive that its pillars resemble the columns of an ancient cathedral, except this one was built to withstand the fury of nature. Welcome to Invisible Structures. Today, you'll discover how the largest underground flood control infrastructure on the planet works, a system that has already prevented billions of dollars in damage and saved countless lives since it opened in 2006. And here's the question that will guide everything. What would happen to Tokyo if this system failed for just a few hours during a typhoon? But before we descend into this underground world, subscribe to the channel now and turn on notifications so you don't miss the next videos. Because here on Invisible Structures, you'll discover the most astonishing feats of engineering hidden around the world. And the next structure we reveal may be right beneath your own city. Get ready. What lies beneath Tokyo is not just concrete, it's survival on a gigantic scale. Tokyo is a technological powerhouse. Earthquake-resistant skyscrapers, bullet trains that run seconds behind schedule, urban systems planned with surgical precision. But there is one force that ignores all that organization: water. And the problem begins with geography. Much of the Tokyo metropolitan region sits on a vast alluvial plain, land formed by river sediments deposited over thousands of years. It looks stable, it looks solid, but in reality, it's naturally prone to flooding. In some districts, the ground sits only a few meters above sea level. And here's the critical detail. Some areas of Tokyo, Nagoya, and Osaka are already below sea level, protected only by levees and massive pumping systems. Now imagine this scenario. A typhoon from the Pacific hits the region. Winds over 150 km/h, storm clouds unloading extreme volumes of rain. In October 2019, Typhoon Hagibis dumped more than 240 millimeters of rain over the Tokyo region in just 24 hours, the highest total since records began in 1976. In mountainous areas like Hakone, 922.5 millimeters fell in a single day, the highest 24-hour rainfall ever recorded in Japan. Sounds small? It isn't. That's 240 liters of water for every square meter. Now multiply that across hundreds of square kilometers of urban land. We're talking about hundreds of millions of tons of water falling almost at the same time. And all that water has to go somewhere. But modern Tokyo is covered in concrete, asphalt, and buildings. The natural soil that once absorbed rain has been replaced by impermeable surfaces. It's like pouring water over a massive concrete slab. It runs off, fast. That water rushes down from the mountainous areas north and west of the city and flows into rivers like the Arakawa, Nakagawa, Edo, and dozens of smaller canals. Dozens of waterways cut across the metropolis. When the volume rises too quickly, river levels can surge in minutes. And here's the problem. Many of these rivers are relatively narrow for the size of the basins they drain. When rain is intense and continuous, the natural system simply can't handle the flow. Historically, this has happened many times. In September 1991, Typhoon Mireille, the worst in 30 years at the time, flooded 30,000 homes and about 100 square kilometers of land in Tokyo's northern suburbs, causing 52 deaths. Throughout the last century, floods repeatedly devastated entire neighborhoods. Houses were submerged to the roof. Critical infrastructure shut down. In some events, economic losses exceeded billions of dollars. Typhoon Hagibis in 2019 caused Y21186 trillion in damage, about $17 billion, the largest loss from a single non-tsunami weather disaster in Japan's recorded history. There were 139 deaths, 142 levee failures across 71 different rivers, and more than 80,000 buildings damaged. 10 bullet trains were completely submerged at a rail yard in Nagano, resulting in $32.8 billion in losses just to replace the trains. And this happened in one of the strongest economies on Earth. Now add climate change to the equation. The Japan Meteorological Agency reports that intense rainfall events have increased by about 70% across the country, a trend linked to global warming. Japan receives nearly twice the global average rainfall, and Tokyo is especially vulnerable during typhoon season. Extreme storms are becoming more frequent and more intense. Rainfall concentrated in just a few hours, once rare, now happens far more often. And there's another factor people rarely mention. Tokyo is extremely dense, one of the largest urban concentrations in the world. When flooding happens, it doesn't just affect streets. It affects subway systems, shopping centers, hospitals, electrical grids, and telecommunications networks. A single day of disruption can cause enormous financial losses. Businesses shut down, transportation stops, supply chains break. And now comes the part that changes everything. In 1992, shortly after the disaster caused by Typhoon Mireille, Japanese engineers decided it was time to build something radical, something invisible, something that wouldn't compete with the city for space at the surface. They decided to go underground. And if this kind of urban engineering impresses you, drop a like right now. It tells YouTube you want to keep watching content about the largest hidden infrastructures on the planet, here on Invisible Structures. In the next section, you'll see the structure that looks like a secret concrete cathedral, the true flood control heart that keeps Tokyo running. On the surface, you see an administrative building, a soccer field, a few trees. Nothing that suggests the largest underground flood control structure on the planet is hidden there. But Tokyo's real battle against water begins about 50 meters below ground. You descend roughly 50 meters down a narrow metal staircase. The air grows colder, the sound changes, and then, suddenly, the space opens before you. Each pillar stands 18 meters tall, the height of a 6-story building. There are 59 massive concrete columns, each weighing 500 tons, lined up in perfect rows. The ceiling is so high it disappears into shadow. Footsteps echo like they would inside an ancient temple. It's no surprise this place earned a world-famous nickname, the Underground Cathedral, or, as it's known in Japan, the Underground Temple. But this is not a symbolic monument. It's a hydraulic machine disguised as one. The structure is part of a system officially called the Metropolitan Area Outer Underground Discharge Channel, better known as GCANs. The project began in 1992 and took 14 years to complete, finally opening in 2006. The total cost was about $2.6 billion, an investment many people at the time considered excessive. But the engineering behind it is extraordinary. The system is made up of 5 enormous vertical silos. Each one measures 32 meters in diameter and 65 meters deep, like burying a 20-story building upside down. They're so large that the Statue of Liberty or even a space shuttle could fit inside each one. These silos work like gigantic funnels. When the level of one of the 5 monitored rivers, Nakagawa, Kuramatsu, Otoshi-Furutone, Channel 18, and Yukimatsu, reaches a critical point, floodgates open, and the water is redirected into these colossal shafts. The current spirals down to the bottom, where it meets the main tunnel. That tunnel stretches 6.4 kilometers and measures about 10 meters in diameter. Large enough for a truck to drive through, it sits 50 meters below the surface, deeper than most subway systems. Building these tunnels required a breakthrough. Japanese engineers developed a new method for joining concrete segments using wedges instead of bolts, dramatically reducing construction time. The technique later became standard in major tunnel projects around the world. The tunnel connects all 5 silos to the main chamber, the famous underground temple. This chamber has astonishing dimensions: 177 meters long, 78 meters wide, and 25 meters high. To picture it, imagine placing an entire soccer field beneath the ground. And here's something many people don't realize. The 59 pillars aren't there just to hold up the ceiling. They serve a critical hydraulic function. The water arriving here cannot simply be pushed forward unchecked. If the pressure becomes unstable, the impact could compromise the entire system. So the chamber acts as a hydraulic stabilizer. The pillars dissipate the energy of the water, breaking the force of the flow before it moves to the final stage. Imagine an entire river entering a concrete hall and being slowed with millimeter precision. Each pillar also helps counter buoyancy, the tendency of the empty tank to be pushed upward by the pressure of surrounding groundwater. Without these massive columns, the chamber itself could be displaced by geological forces. During severe storms, the system can temporarily store up to 670,000 cubic meters of water, about half the capacity of the Tokyo Dome. It's like holding a hidden underground lake until it's safe to release it. And all of this happens while, above ground, the city keeps moving. People cross streets, trains run, lights stay on, unaware that dozens of meters below, an artificial river is being controlled in real time. Now I want to know from you. Would you dare walk through this underground cathedral, knowing that, during a real storm, millions of liters of water could rush through that space? Leave a comment below and tell me which city and state you're watching from. I want to map where people fascinated by these invisible megastructures are around the world. Now, imagine the sky darkening over Tokyo. Weather alerts have already been issued. A typhoon is approaching. The forecast calls for intense rainfall in the coming hours. But even before the first street begins to flood, the underground system is already on alert. Across rivers and canals throughout the metropolitan area, sensors track water level, pressure, and flow. They constantly monitor the behavior of the water. Every change of just a few centimeters is recorded in real time. The data is sent directly to the operational control center. There, engineers watch screens filled with graphs, digital maps, and glowing indicators. They don't wait for flooding to happen. They anticipate it. When a river reaches a predefined critical level, automated floodgates begin to activate. The water isn't simply diverted, it's calculated. The system determines exactly how much volume can be redirected without destabilizing the main rivers. Massive gates open, allowing water to plunge vertically down the silos. The descent is violent. Millions of liters spiral downward, generating immense force. Each silo can receive up to 100 cubic meters of water per second. At the bottom, the current enters the main tunnel and moves toward the stabilization chamber. There, the 59 pillars work to calm the violent flow. But the final stage is still ahead. The pumps. And these are no ordinary pumps. The GCAN system uses 4 industrial turbines powered by 14,000 horsepower engines, comparable to the power of large ships. When activated, they can move 200 tons of water per second. Let me repeat that. 200 tons every second. To put that in perspective, that's enough to drain a 25-meter Olympic swimming pool in just 3 seconds, or 12 Olympic pools in under a minute. These pumps push the accumulated water into the Edo River, a much larger river designed to receive extreme volumes without overflowing. It's like redirecting a liquid avalanche in a controlled way. And all of this happens while the storm is still unfolding. This is not a system that reacts after disaster strikes. It operates during the chaos. But there's an extraordinary technical challenge here. If the pumps start too early, capacity may be wasted. If they start too late, the risk grows dramatically. That's why algorithms and mathematical models help guide the decisions. The system combines weather forecasts, historical flow data, and real-time river levels to calculate the ideal timing for every step. It's predictive engineering. During major storms, a team of about 30 operators monitors the system minute by minute. Adjustments are made in real time. It's like conducting a hydraulic orchestra under maximum pressure. Since entering operation in 2006, GCANs has been activated an average of 7 times per year. By 2014, it had already operated 85 times. The system continues to run regularly, in some years even more frequently as extreme weather events increase. During Typhoon Hagibis in October 2019, the system faced its most severe test. The Nakagawa River Basin north of Tokyo received 175.7 million cubic meters of water in just a few days. GCANs drained 27% of that volume, nearly 47 million cubic meters. Even more important, the system reduced the critical period from 28 hours to just 4 hours, the time the water level stayed above the warning threshold. Without GCANs, entire areas of Saitama and Tokyo districts like Adachi, Katsushika, and Edogawa would likely have been severely flooded. If you're finding this incredible, share it with someone who loves engineering and fascinating facts about cities. Knowledge like this deserves to spread. Now imagine Tokyo without this system. Without the 5 underground silos, without the 6.4-kilometer tunnel, without the concrete cathedral, without the giant pumps working silently during a typhoon. The result would be immediate. Entire neighborhoods could flood within hours. Underground subway lines could turn into artificial rivers. The economic impact would be measured in tens of billions. And here's a detail many people don't know. Studies estimate the system has already prevented about 148 billion yen in damage, roughly $1.3 billion, since it opened. That turns this project into something far beyond a drainage structure. It's a long-term investment, an insurance policy made of concrete. And it's not just about money, it's about continuity, about keeping a metropolis of 37 million people functioning even when nature launches its worst attack. Maybe the future of megacities isn't only in smart skyscrapers, but in invisible megastructures working silently beneath the surface. Because while the surface shows lights, movement, and technology, the real shield may be hidden underground. But engineers warn that even advanced systems have limits. And there's another fascinating detail. Qanats has unexpectedly become a tourist attraction. Every day, visitors from around the world descend into the underground temple to see this concrete cathedral up close. But the popularity serves an educational purpose. It reminds people that infrastructure matters, that the invisible structures beneath our feet can be just as critical as the skyscrapers above our heads. And that completely changes how we see a modern city. The next time you see Tokyo facing a typhoon and still functioning almost normally, remember, a concrete cathedral is holding back an artificial river 50 meters beneath people's feet. And that may be one of the greatest proofs that engineering is not just construction. It's prevention, it's calculation, it's long-term vision, it's survival. If you made it this far, you now know that behind every resilient metropolis are structures almost no one sees, yet they make all the difference. So tell me in the comments, which part of this system impressed you the most? Do you think your city would need something like this? And where are you watching from? If you want to keep discovering the world's most incredible hidden infrastructure, subscribe to Invisible Structures. Because behind every modern city, there's an underground story waiting to be revealed. And the next one might be much closer than you think. And now that you've seen how an underground river protects Tokyo from flooding, you might be thinking, there's nothing like that in my city. But there is. It may not be the size of a buried stadium like in Japan. It may not have giant concrete columns like a hidden temple. But there is an invisible structure working beneath your feet. Every time it rains, every time water disappears into a storm drain, every time the city keeps moving. In the next video, you'll discover where rainwater goes before floods begin, and how tunnels and reservoirs no one ever sees may be protecting your own city right now. After watching it, you'll never look at a storm drain the same way again. Subscribe to the channel because here we reveal the invisible structures that keep the world running. And in the next episode, the story continues underground.